Okay, so this is lecture 9. Let's go to our previous lecture. So in the previous lecture, lecture 8, we have discussed about the non-ideal IV characteristics of our MOS transistor. So here non-ideal means that when we have short channel device. So the main body of our previous lecture 8 was devoted to the velocity saturation effect, and as a result of that analysis we have found that the saturation velocity is given by this form. So here VZT is gate overdrive voltage, so this is quite typical for our consideration. So in the case of long channel MOSFET, this determines the position where we have transition from linear region to saturation region. So, however, when we have a very short channel length, then this L decreases, and also this critical voltage decreases, and this form of saturation velocity is simply given by taking the smaller one between gate overdrive voltage and critical voltage. So if we have a sufficiently short channel device, then we will have saturation velocity or saturation voltage corresponding to our critical voltage. So that was the situation we have considered in our previous lecture. So that is simply meaning that early saturation occurs due to the velocity saturation. And at the end of our previous lecture we have thought about body effect, and when we have this PN junction between source and substrate and drain and substrate, if we apply negative bias to this one, so if we apply a body voltage which is lower than 0, then this PN junction is placed in its reverse bias, and also it is placed in its reverse bias, so no current is allowed through this junction, PN junction. And another effect is when you have the negative body bias, then we will have increased threshold voltage. So threshold voltage is increased when we apply the negative body voltage. So by controlling this body voltage efficiently or in a smart way, then we can control the power consumption of our transistor. That was our previous lecture, and I remember that we have discussed something about the subthreshold slope, so I just wanted to repeat this important discussion once again. So this figure shows ID versus VGS curve. So simply speaking, this is input characteristics, and that is written in semi-logarithmic scale. So Y scale is logarithmic drain current, and x-axis is just a linear gate voltage. So now typically we can see certain kind of slope here, and that slope is really important. So as I told you before, so subthreshold slope is defined as this form. So of course here we have inverse. So what is it? This is simply given by slope. So if we consider this way, if this is log 10 over ID and this is VGS, actually this quantity itself determines the slope, but usually we wanted to take inverse of it. So if we have large subthreshold slope. It means that in this graph, in this input characteristic graph, this is corresponding to high subthreshold slope case. And if we have a very small subthreshold slope, then that is corresponding to almost a vertical line for this one. However, this is not possible because this is prohibited by law of our nature. So there is certain limitation. And how can you express this limiting value of a subthreshold slope? It is given by this form. Of course, here we have a certain unknown number n. So who decided this number? So I will explain it later. However, here we have a VT. This is not threshold voltage, but this is summer voltage, and this is about about 25 volt in the case of 300 Kelvin, and log 10, that is just a number about 2.3. So combining them all, I mean that combining this summer voltage and log 10, then we can find a certain number, because this log 10 is just a number and summer voltage is voltage, their product is still a voltage. So what we can have here is simply given by certain voltage, and this voltage is corresponding to approximately 60 millivolt. So simply speaking, at 300 Kelvin, we can say subthreshold slope is just n times 60 millivolt per decade. So why do we have a decade here? Is it because we have already done this log 10, and here we have a certain number. So depending on this number, we have a different slopes. For example, if this is 1, then we will have almost ideal number like 60 millivolt per decade. And if we have a number close to, this is quite a bad situation, so it is difficult to think this kind of value in these days, but then we will have 120 millivolt per decade. Usually we wanted to have a value of n much smaller than number 2. Okay, so anyway, simply speaking, if our subthreshold slope, so it was just explained in our previous lecture, but I wanted to repeat it once again. Let's consider a case like our subthreshold slope is 60 millivolt per decade, and we wanted to have at least I on and I off value higher than 10 to the 3, so larger than 1000. Then at least how large should be the VD? It means that at least the VDD should be larger than 180 millivolt. In order to have at least 3 orders of difference between off current and on current, we need 3 times of our subthreshold slope. Then instead of that, now we can consider a little bit degraded case like 90, for example. In this case, what will happen? Instead of this 180 millivolt, then we have to have 270 millivolt in order to get 3 orders of difference between I on and I off. So simply speaking, this subthreshold slope determines the minimum voltage, minimum allowed voltage between the 0 and VDD. So if we have a steep line here, then we can have small difference. However, if we have a more degraded slope here, then we need much wider voltage range to increase our current. So that's the reason why we wanted to minimize this subthreshold slope. However, subthreshold slope is just a function of n, and who decide or which effect determines this n value. So this n value is determined by the ratio between our oxide capacitance and substrate capacitance. So what is it? This is capacitance originated from our p-type substrate in the case of n MOSFET. So simply speaking, it means that if we have no substrate, or when substrate is fully depleted, then that will go to 0. So our subthreshold slope will approach its best value, 60 mV per decade. On the other hand, if we have certain substrate and which is not fully depleted, then our n value will be always larger than 1. So we will have a degraded subthreshold slope for our planar MOSFET. So how about the state-of-the-art devices? Our state-of-the-art devices has no substrate contact in it, so therefore its subthreshold slope is quite close to 60 mV per decade. So already we have achieved the best thing we can do in these days. However, people really wanted to increase this or reduce the subthreshold slope even further, but that is not possible with conventional CMOS technology. So that's the reason why we have a lot of works on steep slope transistors. But that is another story, not related with this design course. And here, up to now, I have explained the thing related with this slope. So best thing is to have quite a steep line. However, there is a certain limitation. Please remember this limiting value. What was it? That was 60 mV per decade. And here we have another two things to be covered in this course. One is so-called dibble, and another one is giddle. So I'm not kidding, this is the official names for these effects. So dibble and giddle. So what is the dibble? Here, drain induced barrier lowering. So what is it? Think about this one. Here we have two curves. Now this curve really works. So usually we consider this curve output drain voltage is biased to 1 or VDD. So here we wanted to have I on current, and here we wanted to have I off current. However, we need another curve corresponding to the input characteristics with a small VDS value or a low VDS value. So why should we have this kind of thing? Because in order to measure this quantity. So are you with me? Although here in this graph taken from our textbook shows this one, but please neglect it. So usually dibble is measured as the difference of voltage. I mean that, for example, think about one 100 nanoampere per micrometer. For example, let's see this one. Select a certain value and say that in order to achieve this same value of drain current, how much the gate voltage should be applied. In the case of VDS equal to 0.1 case, we needed the voltage almost close to 0.2. However, when we have drain voltage quite close to 1.0, then our required gate voltage is just about 0.05 or whatever, so certain value. So you can immediately understand we have about 0.15 volt difference when we have VDS equal to 0.1 volt and VDS equal to VDD. So what happens? If everything is so ideal, then maybe that will be the case. I mean that if everything is ideal, then when we draw log 10 of ID and VGS, once again input characteristics in semi-logarithmic scale, then at least in this subthreshold region, two curves will be identical. Here, what are they? One is the curve obtained from VDS equal to VDD case. Another one is corresponding to VDS is quite close to 0. So simply speaking, if the transistor is ideal, whether you apply high voltage or you apply low voltage should not make any difference in your subthreshold current. In this range, your current does not depend on what? Depend on the VDS value. That is our ideal case. However, as you can see here, clearly, when you apply higher voltage, now you have the shift of your voltage to achieve same amount of current. What is it? Then simply this yellow curve reveals that due to the action of your drain voltage, the control of your gate over the channel region is reduced. So now even drain voltage has some effect on your current level. So that is the realistic case. This is a very bad case. I mean that here we have source, drain and gate here, and this part, this channel region is controlled by this gate region. We wanted to give the full control over this channel region to the gate. Gate should be the king of this field. However, this graph shows that although gate says that no current at all by applying VGS smaller than threshold voltage, but when VDS equal to VDD, now we have small additional amount of current flowing between source and drain, although gate does not allow it. So this dibble, so-called dibble, is regarded as a best measure to visualize or quantify the amount of controllability of our gate. So if this dibble is high, so simply speaking, we just measure the voltage shift here. If this voltage shift is high, then dibble is high and this device is a bad device. And if we have a low dibble, then this device is regarded as a good device. Are you with me? Okay. Then think about this one. Which device will have a lower dibble and better dibble characteristics? So I will just give you two representative devices. One device. They are from the same technology. Think about this device. Then another device. Which one has better control of gate over the channel region? Or which one has weaker controllability of drain over channel region? So you can understand that in this case, drain is too far from source. So although we increase this value, but that does not change the current value. However, in the case of this short channel device, then changing the drain voltage can affect this source region too. So that will have bad dibble characteristics expected, and this is good dibble characteristics. Okay, so now you have to draw this kind of graphs. So as a function of gate length, you just draw dibble. Then what you get typically in this case is just like a flat line. Then it is just increasing quite rapidly, just nearby the minimum channel length L. So actually, why do we have this kind of behavior? It is because, the minimum size of your channel length is more or less determined by the position where we have high dibble case. So simply speaking, if we have this kind of behavior, then we will say that this is the allowed minimum L value. And if our device just looks like this, then maybe we can try even shorter channel length. Okay, so actually dibble is a kind of showstopper. Show means that the show reducing the channel length. However, the channel length is actually limited by this dibble. So dibble quantity is quite important, because why it is important? It just represents the controllability of our gate, or competition between our gate and drain. And we want to have the reasonable value which is almost fully controlled by gate only, not severely affected by drain. So this is quite important. Another one is giddle. So sounds like quite similar like dibble, but this is a completely different one. And this is so where can you find the giddle? Dibble is found in this subthreshold region, and we wanted to consider it in its positive gate bias voltage in MOSFET case. But giddle is just appeared in this 0 or negative part actually. So here we wanted to have just ever decreasing curve when we decrease the gate voltage. However, there occurs certain kind of leakage current which is not expected here. So this curve is originated from this Giddel phenomenon. Okay, so then what is the physical origin of this Giddel phenomenon? That is attributed to the band-to-band tunneling inside the silicon, but I will not cover that physical mechanism. But anyway, there is another mechanism. Then my question is, how about this one, this guy? How about dipole? What is the physical mechanism of a dipole? There is no special physical mechanism to introduce a dipole. This is more related with their structure. So electrons and holes are moving in their normal way, following the thermal excitation and driven by electric field and diffuse. However, in this case, due to two short channel device, then we have increased current. So here we have just normal transport, conventional transport, and here Giddel is originated from a special thing called as band-to-band tunneling. Okay, they have a different physical origin. Okay, so I think that this is the end of our discussion on MOS transistors. So now let's go to the inverter. So although that is written as DC transfer, this part is devoted to our CMOS inverter. So now consider a CMOS inverter. So here we have a CMOS inverter, it's a schematic, and here we have a input and output. Output is just drain of M MOSFET, at the same time drain of P MOSFET. So this is P MOSFET and this is M MOSFET, and source of M MOSFET is grounded and source of our P MOSFET is connected to VDD. So maybe you remember that when we apply logical value 0, logical low, then it becomes VDD, and when we apply VDD, then it becomes 0 volt. That was our previous discussion. Why? In this case, if we apply 0 volt, now our N MOSFET is completely turned off, and now instead our P MOSFET is fully turned on. So we have a good electrical connection between VDD and V out. So it becomes VDD. So same applies to our VDD and 0 relation. I think that all of you understand this one. However, the point is, up to now we have thought about these two extreme cases, okay, 0 and VDD, certainly copied to VDD and 0. Then how about the intermediate value? So if we draw this graph in and out, now what we know certainly is, okay, here we have one point corresponding to 0, VDD, and we know some point corresponding to VDD, 0 volt. Then my question is, how about the curve in between? So is it looks like this, or is it looks like this? How about the voltage transfer curve? This curve is usually called as voltage transfer curve, and we wanted to discuss about its shape. Of course, in this CMOS inverter, the ideal shape would be like this. Maybe this is the ideal one. Sorry about this small difference, but you know, this is just attached to exactly 0. So up to here, maybe preferably about half VDD, then that is just regarded as a logical low, and beyond that value, so that is regarded as a logical high. That would be quite a good situation. But think about a little bit degraded one more realistic one, like V in and V out. And of course, here we have two fixed points, and now think about this kind of. Well, if we have this piecewise voltage transfer curve, then what will happen? If we have this kind of thing, then up to this voltage, then logical low value is mapped onto logical high value. Wow, that is the inverter operation. And also beyond this value to VDD, we say that high value is mapped onto logical low value. Once again, this is a proper logic operation. However, in between, in this case, we have some gray region, which is not completely low and completely high. So it is difficult to say that what is it? Is this low, high? So a little difficult. So we will talk about this one in this lecture. Before starting today's main content, just let me summarize the important properties of a CMOS inverter. I took it from other Labai's books, so not our textbook, but anyway, you can easily understand these factors. Okay, high, logical high and logical low is corresponding to VDD and ground respectively. Okay, it is quite easy. And here, logic levels are not dependent on the relative device sizes. So think about this one. Now we have small P MOSFET and very large N MOSFET. So sorry about this ugly drawing, but please regard it as weak P MOSFET and strong N MOSFET. Now think about this one. What will happen? How about your out value? Now this guy is quite strong. Yes, everybody understand. For example, 100 times stronger than this weak P MOSFET. Now we apply 0 volt. Then what will happen? What is your expectation about your V out? Okay, since N MOSFET is quite strong, even in the case of 0 volt, do we have 0 volt? Actually, not. Although this is 100 times larger or stronger, but still this 0 volt completely, perfectly shut down this strong N MOSFET. The remaining thing is, although that is quite weak, but still the only P MOSFET is connected to the V out, so our V out will be safely VDD. So simply speaking, logic levels, in this case VDD and ground, does not change when you change your N MOSFET and P MOSFET. That is the situation. Okay, so are you all with me? Then can you find any kind of counterexample for this behavior? I mean that is there any logic gate which really depends on the transistor size? Can you make it? So yes, you can simply make it by this kind of pseudo-MOS. Okay, now think about this one. Let's say this is an inverter and we wanted to apply 0 volt over VDD. Then please think about this one. Now when we apply 0 volt to its input voltage, then this MOSFET will be shut down. Although this is not PMOSFET, just a normal resistor, but still this one has a finite resistance RD. Then what will happen? The only available electrical connection is this one. So we will have output voltage exactly equal to VDD. Okay, good. However, think about this one. When we have VDD, now VDD, then our transistor is now turned on. Now this MOSFET try to pull down the output voltage. However, make a comparison between our CMOS inverter. In the case of CMOS inverter, what happened? In the case of CMOS inverter, when we have a VDD, then also our MOSFET is activated and connected to Vout. Good. However, in the case of our CMOS inverter, there is no electrical connection in this pull-up network. It is completely shut off. So, from the viewpoint of this Vout, it has the only electrical connection only toward ground. Then now think about this case. Now, MOSFET provides certain strong connection, but still RD has also certain connection, although not as strong as MOSFET, but here we have connection to VDD. So now the output voltage will be determined by the balance between this MOSFET path and this resistive path. Okay, if this MOSFET is quite strong, then our output will approach to 0. And if this MOSFET is not that strong or just comparable to RD, then what will happen? Then our output value will be just in between 0 and VDD. Okay, so are you with me? So simply speaking, when we just draw our voltage transfer curve once again, V in, then ideal case, ideal CMOS inverter, we have this kind of behavior. At least these 2 points are fixed. But in the case of this is MOS implementation, then what we can have is this MOS part is okay. So this low input case is okay, but high input case we have different values and different values. Who decided this final output level? Actually, your MOSFET determines the output level when you have this input equal to VDD case. So in that case, we must be very careful about this ratio. So size of your transistor really make a big difference. However, fortunately, in the case of a CMOS inverter, you don't have to worry about it. Whether you have a small NMOS or large NMOS, still it is guaranteed that at least you have this value and this value in your voltage transfer curve. So are you with me? So then let's go to the third one. A well-designed CMOS inverter has a low output impedance. So let's just consider it. I think that this can be well explained by this graphs. So let's go to our graphs here. The output impedance simply means that the impedance seen from this output node. Then what is seen from this output node? Then of course we will have a very high impedance through this VDD. On the other hand, through this ground, we will just have the resistance originated from the turned on and MOSFET. So what is it? It will be quite small because N MOSFET is fully turned on. So that will be quite small. So can you estimate its value? So or can you, for example, write down the Rn value of your MOSFET? So let me just do it together with you. So my question is, okay, in this case, please try to say what is the operational region of our MOSFET. Is it in sub-threshold region, or is it in linear region, or is it in saturation region? What is your expectation? So this one is corresponding to input voltage equal to VDD. Okay, so since input voltage is so high, we can safely neglect this one. Then how about your choice between linear and saturation? In this case, Vout is also close to 0 volt. Then what is your answer? Gate is VDD and drain is 0 volt, so the device in its saturation mode. So if the device is saturation mode, then you can write down in this way: mu n Cox W over L. In the case of a long channel MOSFET, then now you can have VGS minus VT minus VDS and VDS. Here we have half of it. So now we can have this form. However, when we have a very small VD, then this second order term goes away, so we can safely neglect it. Then our result will be like this. ID can be just a linear function of VDS. Then please write down the expression for our R sub n. What is it? That is simply given by 1 over mu n Cox W over L VGS minus VT. That will be the expression for our Rn. And now in this case, what is it? VGS. VGS in this case is really VDD minus VT. This is quite a high value, so we will have quite low Rn value. So that's the reason why a well-designed CMOS inverter has a low output impedance. In both cases, for example, this is output low and this is corresponding to output high. In both cases, we have a good connection from output node to either ground or VDD. So from the impedance point of view, we have a good connection and low impedance that is explained here. On the other hand, up to now we have considered output impedance. Then how about impedance? So input impedance in this case, so when we consider low frequency, instead of impedance we can say input resistance, then that is extremely high. Why we have extremely high input impedance? Then in order to consider this input impedance, now we have to consider impedance seen from this input node. Then what is seen from this one? Then now we can go to this MOS path, and what is seen in this case is just a capacitance. And from this PMOS path also we can see just a capacitance. Then what is the capacitance seen from this gate part? Of course, there will be certain capacitance coming from oxide capacitance. So this is the per area oxide capacitance, and this is the width of your transistor. Also, you will have Cox WP times LP, so in the case of your PMOS band. So simply speaking, you will have almost pure capacitor connected to your transistor. So now, that it can be written as this form. Simply V in, and it goes to certain capacitor, and that is grounded. And when you go to the PMOS path, we also see another capacitor, and that is connected to our VDD. Then we are now asked to answer what is the impedance of this gate seen from this gate terminal. In the case, if we are working at low frequency, then it contributes very high impedance, and also this one contributes very high impedance. So this impedance seen from our input node will be quite high. So please go to this one. This one is valid at low frequency. If we go to high frequency, then what will happen? If we go to high frequency, then each of them, this capacitance and this capacitance, will give us a finite, much smaller value of impedance. Actually, it's imaginary part, but that will contribute the impedance. So finally, the absence of current flow between VDD and ground means that the logic gate does not consume any static power. So static is important because static power, and there is another power consumption called as dynamic power consumption, and this dynamic power consumption is obtained from the switching operation. You turning on and off, then you have to spend something. And static power means that you just turn it on or turn it off in some cases, then just to count the power consumption spent by this DC bias condition. So in the case of DC bias condition, in both cases, we have no direct connection between our VDD and ground. And please have a look at once again this output high case. Even in this output high case, we have no electrical connection between VDD and ground. Okay, so therefore there will be no current at all, and also no current at all. Why? Because now this one becomes just VDD, so there is no voltage difference and there will be no current flow. So simply speaking, no power consumption in the case of our static power consumption. That is critically important. Why that is important? Previously, the CMOS was not the major technology. Before we introduced CMOS technology, there was another technology called bipolar junction transistor, and it is quite good in a sense of its operational speed. It is quite fast even compared to the CMOS technology. However, eventually now we have just CMOS technology all over the world. Why? Because this BJT technology have some non-zero static power consumption. It means that although you don't perform anything for this device or this circuit, but your circuit just consume the energy, then is not good for this mobile era. So we need a certain thing which can be handheld everywhere. So that's the reason why now CMOS is just a major technology of our world. Okay. So now I have covered quickly about the important points of this CMOS inverter. Then now let's cover our lecture material. So now we have the voltage transfer curve of our CMOS inverter. Then you can see the graphs like inverter. Of course, as I told you before, the ideal would be like this. That would be the ideal case. But although not perfect, but you can understand it is much better than something like this. So please make a comparison. This red colors from CMOS inverter and blue one from other way to implement an inverter. So you can see that at least in this part we have quite much improved value. At least the logic value is always 0 in this CMOS one. Also you can see that this is quite steep here. We have a very steep line here. Then please identify the operational modes of these transistors. Here we have voltage even lower than MMOS threshold voltage. Then what will happen? Now MMOS is completely turned off and only PMOSFET is turned on. So here we have the case NMOSFET is off and our PMOSFET is of course on. But please consider what is it? Is it in the linear mode or is it in the saturation mode? Now PMOSFET has the form like a VDD. Its source is VDD and now its drain is also VDD. So what is the voltage difference between source and drain? It is 0. So if drain to source voltage is 0, then it is certain that our PMOSFET is in its linear mode. Okay, then now let's go to this part. In this part, we have gate voltage even beyond this area. I mean that now our P MOSFET is turned off. Then how about N MOSFET? In the case of N MOSFET, we have a high gate bias and quite low drain voltage. What is it? So that is just in its linear mode. Then if we go to beyond this point, then see what happens. Now when we slightly increase the gate voltage of our N MOSFET and P MOSFET over this threshold voltage of our N MOSFET, then we will have small reduction of the voltage. However, this is quite marginal. So still our P MOSFET will be placed in its linear region, but now our N MOSFET is anyhow turned on and drain voltage is quite high for our N MOSFET. So in this range, we will have N MOSFET in its saturation mode and P MOSFET in its linear mode. And eventually there will be ever decreasing value of our output voltage. Then eventually we will have something like this. For example, think about this point. Then consider our N MOSFET. For example, we just applied half VDD and output is, for example, also half VDD, and this is also half VDD. Then happen to be the drain voltage and source voltage are the same. Then what will happen to this N MOSFET? When N MOSFET has the same value of gate voltage and drain voltage, it is certain that this device is in its saturation mode. Why? Because we must consider whether VDS is larger than gate overdrive voltage or not. Then what was the gate drive voltage? That was VGS minus VT. Happen to be, if we have the same value for VDS and VGS, then always we have this inequality. VDS and VGS, when they are the same, then always the minus VT dictate this direction. So we are always in saturation region. So simply speaking, somewhere here we will have certain position where N MOSFET and P MOSFET, both of them are in its saturation mode. And this is corresponding to the steep change of its voltage transfer curve. Okay, so are you with me? So now you can understand there are 5 operational modes for it. Okay. So now think about this one. The first thing we have to consider is input threshold or switching threshold equivalently. So this is just showing the voltage where input and output are perfectly matched. Usually in the case of this inverter, when you have a certain value V in, then there will be V out, and in general your input is not equal to output. That is quite common. 0 VDD or VDD 0. So in general they are not identical. However, for this special case, so input threshold, then we have same value. Then how can we visualize this value? This value can be just written as or visualized as the cross point, cross section between our normal voltage transfer curve and just a straight line of V out equal to V in. Their crossing point, this point just shows the coordinate corresponding to V in, comma, V in inversion threshold or input threshold. Anyway, so if we have this kind of thing, please try to find out your input threshold voltage. Then what you can do is, this is our VDD and this is our VDD, and just to draw a straight line, then you will find that this is for our switching threshold for this voltage transfer curve. And if we have a different voltage transfer curve, for example, another extreme is like this, then we will have a much different value of input threshold and also much different value. So are you with me? So simply speaking, it's like if you, as a designer, you can design your inverter. Then as a result of your design, there will be at least these 2 points are fixed and there will be certain graphs. So anyway, it really depends on your choice. However, whenever you have such kind of thing, then you will get certain point corresponding to input threshold. Then this one can be regarded as the border between your logical low input and logical high input. So are you agree with me? So now let's think about this one. In this example, let's consider this extreme transfer curve. Then as we have seen about this one, we have our input threshold voltage. Then what is the range of our logical low? Maybe this is regarded as logical low, and this is regarded as logical high. So do you think that this is ideal or not? So this is seemingly quite a bad one. So when we have a random value from 0 to VDD, then there is more, it is more probable that random voltage is regarded as logical low. That is quite a bad one. Also, we have another different extreme. In this case, now we have much limited values for limited range for logical low and much wider values for logical high. This is also not good. So simply speaking, the ideal case is this input threshold should be quite close to just half VDD. If that is close to half VDD, it means that our inverter is more or less balanced between logical high and logical low. That is our first consideration. So we just wanted to make it close to half VDD. Then who decided? Which one is decided? This one. So of course, in every case, even in these skewed cases, it is certain that we have well-defined logic values and well-defined logic values. We are not talking about these points. We are now talking about the transition point, first of all. Then who decided this shape? It means that here these intermediate points are obtained from the competition between our N MOSFET and P MOSFET. Okay, so starting from here, MOSFET was completely weak due to the input voltage, and now it becomes stronger and stronger and stronger. Eventually they become comparable, and now this one is MOS dominated one. So you can understand this point is, this range is determined by N MOSFET. When N MOSFET is strong, then we will have this behavior. And when P MOSFET is strong, or pull-up network is strong, then we will have this behavior. So we have ratio beta P over beta N. Here beta and beta is corresponding to just W over L times mobility COS. Usually both of NMOS and PMOS share the same oxide capacitance in the same technology, so they are common. So a difference comes from the width, length, and mobility. And when they are different, for example, when this beta is 10 times higher or 10 times larger than N MOSFET, then we call it as strong, relatively strong P MOSFET. And if this is 0.1, then we say that relatively strong N MOSFET. Then what happens? If we have a strong P MOSFET, then we will have much wider range of PMOS dominated voltage transfer curve and relatively short range for our NMOS dominant curve. So that's the reason why we have this kind of skewed behavior for PMOS dominant. And on the other hand, if we have weaker PMOS, so NMOS is dominant, then we have a wider region for our logical value 0 as an output, then we have a relatively short range for our logical value high. Okay, so I think that you can understand. So then this slide here I just summarized two cases. One case is long channel IV, and another one is the IV characteristics with velocity saturation. So here please have a look at, I have used the saturation mode expression, and please come to here. Then you can also see that I assume that both of our MOSFET and PMOSFET are in their saturation mode. How can you justify this assumption? It is because we are now considering to find out the condition of V in equal to V out. In this case, it is certain that in both cases means that the MOSFET and PMOSFET are in saturation mode. Okay? So now you can see that now this input threshold can be written as the ratio between our MOSFET and PMOSFET. Also, here we have certain ratio between our PMOSFET and MOSFET, and that is the expression. So I will not cover the detail of these expressions. Please do your derivation when you come back to your laboratory. Then we can make this kind of a comparison. If we have a long channel IV characteristics, and let's say that if MOSFET and PMOSFET are perfectly balanced, then what will happen? In this case, of course, in both cases, we will have just half VDD. In this case, when R equal to 1, I mean that perfectly balanced MOSFET and PMOSFET, then our input threshold will be just half VDD. This is quite an ideal case. But now, if we go to this direction, then we are now introducing strong P MOSFET. So strong P MOSFET just to increase the input threshold, and now we have two different behavior limited by velocity saturated inverter and long channel one. As you can see, which one is better? So ideal case, what we wanted to get is just to have completely flat line. Whether you have quite unbalanced design or not, still you wanted to get this condition. However, of course, it is just an ideal one. So if we have unbalanced design for our CMOS inverter, then obviously we have a deviation here. Then long channel IB case has much moderate increase compared with this velocity saturated one. So I think that this is a better one. But why do we have a better behavior of long channel IB compared with velocity saturated inverter? It is because in our case, in our long channel case, so saturation level, do you remember this one? This level was just proportional to which is its square. And in the case of our short channel MOSFET, that difference was just constant, and they showed relatively less steep increase of current in this case. That's the reason why we have two different behaviors. Okay. So anyway, please think about this one. So now we'll go to so although okay okay I have introduced the homework number 3, but still we have not covered this one. So let's wrap up today's lecture at this point, and in next, not this Thursday, but next Thursday we will keep our discussion on the noise margin. After that, we will move to the delay of our logic gate. Okay, do you have any question?
숙제가 있는 건가요?
No. So that is just postponed. So just enjoy your Thanksgiving holidays and see you next Thursday. Okay. So we have no homework. Okay, that's it.